Okay, so we're starting to prepare for your final exam for Calculus 1, and I pulled some worksheet off the internet for a review for a Calculus 1 final. And the first question in here states, clearly and completely state the definition of continuity of a function f of x at x equals a, and how to use this definition in a problem. Okay, so the definition of continuity: in order for a function to be continuous at x equals a couple things need to hold. First of all, f of a has to exist. And the limit as x approaches a has to exist of f of x, and it has to be the same thing as if we plugged in a into the original function wherever we saw an x. Okay, so we can use that definition to help us see if something is continuous at a value x equals a. So we would show plug in a into the original function, see what value that was. We would look at the limit as x approaches a on the left and the right, show that they are the same value. And then we'll show that that same value is the same thing as f of a. So I put these out here and students had looked at them. And the next question was looking at the fundamental theorem of calculus. Why is this important? Why is this theorem so important? Well, there was two parts for the fundamental theorem of calculus. One of them was if we had the integral, a definite integral from a to b of f of x dx, this was equal to the antiderivative evaluated at the upper bound, f of b, minus the antiderivative evaluated at the lower bound. The other one stated that if we had the derivative, if we were taking the derivative of the integral function, and let's say from some constant a to x of f of t dt, this was just equal to f of x. So this piece here is showing us that the derivative and the integral are inverses of each other. They undo each other. Okay, so I just wanted to go through the other problems that we just skipped. I'm just gonna discuss it really quickly, but you should be able to find the derivative using the formal definition of a derivative. So I might give you one problem and say you need to use the formal definition to find the derivative of that. And so recall, let's just write down what the formal definition of the derivative is, and that's the limit as h approaches 0 of f of x plus h minus f of x all over our h value. Just going to get rid of this just to give us room. So you should be able to apply that, finding the derivative of a function. Number 3 states that you should be able to know the definition of a critical value of a function and how to tell whether the function has a local min or local max or neither at those critical values. Okay, so recall we found critical values when our derivative was equal to 0, and then we had to test values on each side, plugging it back into the derivative of our critical values and see if our function was increasing or decreasing. We saw that if our function was increasing and then decreasing at a critical value, then we had a local max. And if it was decreasing and then we had something that was increasing, we had a local min. If we had something that continued in the same direction, then what was happening, it was leveling out so that our function had a tangent line with a slope of 0 there and then continuing in the same direction. And that wouldn't give us either a local max or a local min. So you should be able to tell where a function is increasing, decreasing. And that was just pretty much what we just did for part 3. And that helped us find the local max and local mins. So we want to find where our critical values are and then test values back into our derivative to see if that derivative was positive, it's increasing. And if its derivative is negative, it's decreasing. You should be able to tell where the function is concave up and concave down. So recall that was where you had to find the second derivative. And we wanted to look at where was this equal to 0 and undefined. And then we plugged values back into our second derivative on each side of those values that we just found, which were possible inflection points. And we saw that if the double derivative was greater than 0, then that we had a concave up function. It'll look like this. And if our double derivative was less than 0, then it was concave down. We locate our possible inflection points by what I just said above and determine whether the function really has an inflection point at each point of an inflection, each possible inflection point. Only time it has an inflection point is when it's changing concavity. And so if it's changing on one side, it's concave up, the other side it's concave down, or vice versa of an inflection point, or then it's an inflection point. If the concavity is the same on both on either side, then it is not an inflection point. Okay, so you should be able to look at limits and solve those algebraically, and you should be able to look at a graph and evaluate limits looking at a graph. So let me just pull this up real quick. And so look at those, take a second and look at those and see if you make sure that you would be able to do those types of problems. Okay, so looking at this limit as x is approaching 4 of x minus 4 all over x squared minus x minus 12. So you really always should start with these limits by going in and doing your direct substitution. And so we're going to go in here and we're going to plug in 4 wherever we see an x. And so we have, actually I'm going to plug in 4. I'm going to put parentheses wherever I see an x. So we have 4 minus 4. We have 4 squared minus 4 minus 12. So I notice my numerator, I get back 0 all over my denominator. 4 squared is 16. And then I have minus 4 minus 4. I'm sorry, minus 12, which makes that go to 0. And so we get that 0 over 0. And so we have an indeterminate form. There's 2 ways that we can approach this. We can do this by factoring. This is telling me that I have a factor in common in the numerator and denominator if I get 0 over 0. And I notice that the denominator can factor as x minus 4, x plus 3. Cancel out our factors, like factors. And so now we're just evaluating this limit as x is approaching 4 of 1 over x plus 3. And so when we go and do our direct substitution in here and plug in 4 wherever we see an x, we get back 1 all over 4 plus 7. I'm sorry, 4 plus 3, which is 7. So question was, could we just use L'Hopital's rule? And yeah, you could go ahead and use L'Hopital's rule. But first you had to show it was an indeterminate form. And it had to be a particular indeterminate form. So sometimes we had to manipulate our functions to be that 0 over 0 or infinity over infinity so that we could use this rule. L'Hopital's rule says that if you get that indeterminate form of 0 over 0, we can look at the derivative of our numerator, which is just 1, divided by that derivative of the denominator. The derivative of our denominator is 2x minus 1. And so now if we went in and we did our direct substitution, wherever we saw an x, we would get 1 all over 2 times 4 is 8, and then that 8 minus 1 is 7. So we get that 1/7. Okay, so you wanted to look at C. If we go in and we do direct substitution for C, we're going to get 2 times negative infinity cubed. So that's really going to negative infinity, that numerator. That denominator, negative infinity squared, well, that's positive infinity. Positive infinity plus 1 is infinity. And so we can technically pull that negative out front, and we got that indeterminate form of infinity over infinity. So we can approach this 2 different ways. Again, we can use L'Hopital's rule, or recall in the past, let me just bring it over here. If we got infinity over infinity, we looked at the term with the highest degree in the denominator, and then we went through and we multiplied this by a fancy 1. And our fancy 1 was the 1 over x raised to that degree of the denominator. So here we would multiply 1 over x squared divided by 1 over x squared. And so we have 2x cubed times 1 over x squared. That's going to leave us with a 2x in the numerator. When we distribute this down in the denominator, though, x squared times 1 over x squared is 1, plus 1 times 1 over x squared is 1 over x squared. So remember, 1 over x as x goes to infinity, and that goes to 0. So this 1 over x squared, as x is going to infinity, that piece goes to 0. And so we're left here with 2 times negative infinity all over 1. So this is going to negative infinity. The limit doesn't exist. If you had used L'Hopital's rule, you were going to have to use that more than once. You'd have to use L'Hopital's rule twice in there to get it in the form that you could see what the limit was as x was approaching negative infinity. And then there was a question about going through the formal definition of the derivative. Let's look at one of those problems. So let's get some room. So let's say we want to find the derivative for f prime of x using the formal definition. When, let's say, f of x is equal to 1 over x plus 1. To find the derivative. Okay, so we're going to look at the limit here as h is approaching 0 of this 1 over x plus h. So we're going to plug in x plus h wherever we see an x here. So x plus h plus 1 minus f of x. Well, this is our f of x term. So minus 1 over x plus 1 all over h. If you went in and you did your direct substitution, you will get your 0 over 0. And so that's not helping us right now. That's an indeterminate form and it doesn't tell us anything. And so we want to manipulate this. And so if you have complex fractions, sometimes getting rid of those complex fractions is what you want to do. So we want to look at the least common denominator of the fractions within the fraction, and we're going to multiply this by our fancy 1. I can see that the least common denominator is going to be this x plus h plus 1, all of that times x plus 1. Whatever I multiply the numerator by, I need to multiply the denominator by. And so when we distribute this to that first term, that x plus h plus 1 cancels, and we're left with just the x plus 1 for that first term in the numerator. Distributing this over here to the second fraction, we're gonna have a minus. I'm gonna need parentheses. The x plus 1 piece cancels. So you're left with the x plus h plus 1. All over, do not distribute this piece. Let's just keep it as it is. So h times x plus h plus 1, all times x plus 1. So let's simplify. Let's distribute that negative and combine like terms in that numerator. And so we have the limit as h approaches 0 of x plus 1 minus x minus h minus 1 all over this h all times x plus h plus 1 all times x plus 1. So notice things cancel out. We have a positive 1 and a negative 1, so those disappear. We have an x minus an x, so those disappear. So after combining like terms in our numerator, all we're left with is that negative h all over what I just said before. Okay, so h's cancel. And so now that h canceled, we can now do our direct substitution, and we should not get an indeterminate form anymore. So you have negative 1 in the numerator. We're going to plug in 0 wherever we see an h. And so we get negative 1 all over x plus 0 plus 1. So that's just x plus 1. All times x plus 1, so x plus 1. So I can see that the derivative function is equal to negative 1 all over. I can rewrite x plus 1 times x plus 1 as x plus 1 quantity squared. So I might have that as a two-part question where I might say, show me this using the formal definition as part A, and part B, show me using the rules of derivatives to help us find that. And so if we wanted to use the rules of derivative, let's just talk about that really quick. F of x equals this 1 over x plus 1. There's multiple ways that we can do this. We can do this by the quotient rule. So remember, the quotient rule is different than how we were using L'Hopital's rule. We can't just take the derivative of the numerator and over the derivative of the denominator. Or we can rewrite this. We can bring that x plus 1 up into the numerator. Let's think of this as a parentheses around that whole thing. If we do that, we can rewrite this as parentheses x plus 1 all raised to the negative 1 power. So now rewriting it this way, we can use the chain rule to find the derivative, which I think might be faster than using the quotient rule. And so our outer function, derivative of the outer function, which is this raised to the negative 1 power, we bring down our power down front. So we have negative 1 in front, all times the inside x plus 1 raised to subtracting 1 from our exponent. So negative 1 minus 1 gives us now negative 2 times the derivative of the inside. Derivative of x plus 1 is just 1. So I can now rewrite this, making my exponent positive by bringing it down into the denominator. So I have negative 1 all over x plus 1 quantity squared. Or if I didn't ask you for that second piece and you had time, you can always check to make sure if you weren't sure if you had the correct derivative using that formal definition. So looking at the graph, we want to look at the find the following limits. And so we're looking at the limit as x is approaching 5 on the left-hand side. And so we want to figure out where 5 is on our graph. And we're approaching it on the left-hand side. So we're getting closer and closer to this x equals 5 on the left. We're trying to figure out what is that y value we're approaching, even if it doesn't exist there. And so notice that that y value that we're approaching is 4. So I could prove that this was discontinuous at x equals 5 just by showing, well, there's two things I could show. I could show that the limit as x is approaching 5 on the right is giving me a different value than on the left, but also it's undefined at that x equals 5. So there's multiple conditions that don't hold in order for it to be continuous. This next one says, look at the limit as h approaches 0 of g of 4 plus h minus g of 4 all over h. So you should recognize that this is saying it's looking at the derivative of 4. So if we were looking at this function, it wants us to find the derivative when x equals 4. So when x equals 4, we're going to need to figure out what that slope is of the line. That slope of the tangent line at x equals 4 is the same thing, because this is a line, as this. So to find the slope, we're going to need 2 points on the line, or 2 points. So let's say this 4, 2 is a point. And I'm just going to choose this value here, even though it's open circle, I'm going to choose that as a point because it's linear there. So let's just choose 3, 0 as a point. And so if I look at the slope between those 2 points, I got 2 minus 0 all over 4 minus 3, which gives us 2 all over 1, which is 2. So the slope of the tangent line of g of x at x equals 4 is 2. So for this next piece, let's look at the following. So we're looking at a couple of things. We're going to go in and we're going to do direct substitution. Let's try that. And so if we do direct substitution, plugging in 6, actually we're coming in on the right-hand side. Okay, so if we're coming in on the right-hand side to 6, notice that we're getting, oh shoot. We're getting back 4. I also know just by rules of limits that I can look at the limit of the numerator all over the limit of the denominator. So we saw as we were coming in on the right of 6 that the y value we were getting is 4. So I have 4 in my denominator. And then plugging direct substitution 6 in for x in my numerator, I got that 6 minus 5, which is 1. So this limit of x approaches 6 from the right of x minus 5 over g of x should be 1/4. And then h, the limit as x approaches 6 of g of x. This one does not exist. And to show that it doesn't exist, if I look at 6 coming in on the left of g of x, okay, so left of g of x, I'm sorry, left of 6 for g of x, that's giving us a value of 1. This does not equal the limit as x approaches 6 on the right of g of x, which we saw in the problem above, that was 4. Therefore, the limit as x approaches 6 is undefined or does not exist.
I have a question.
Okay, so the next page of this review says list all the vertical and horizontal asymptotes of y equals the following. Would I give you that? I don't know if I would give you one where I would just ask you to find the horizontal and vertical asymptotes. I might ask you to graph that, or I might ask you, let's look at the limit as x is approaching infinity or negative infinity, and that would give us the horizontal asymptote of that function. And the vertical asymptotes, those occur where we have values which set our denominator equal to 0, but not also our numerator. I'm not sure if I would give you that problem or not. I would definitely give that to my college algebra students because they need to know how to graph rational functions. Number 3, f of x is a piecewise function. We have x squared minus 8 if x is less than or equal to a, and x squared minus a squared all over x minus a if x is greater than a. So find all the values of a so that f is continuous for all of x. Okay, so let's look at what value of a that would make this function, piecewise function, continuous. Okay, so in order to be continuous, the limit as x approaches a on the left of f of x has to equal the limit as x approaches a on the right of f of x. So let's look at the limit as we're approaching a on the left. If we're approaching a on the left, this is telling me that I'm choosing values of a which are less than a. And that tells me I need to use my first equation in that piecewise function, which is x squared minus 8. So just do direct substitution. If we go in here and do direct substitution, we get this a squared minus 8. If we're looking at the limit as x is approaching a on the right, so this time we're looking at values of a which are bigger than a. So we're coming in on the right-hand side. So that tells me that we need to use this first equation. And if we go in here and we do our direct substitution, I notice that we're going to get that indeterminate form of 0 over 0. So let's reduce that a little bit. And we can factor our numerator. And notice our x minus a's cancel. And so now if we did direct substitution, we would get a plus a, which gives us back 2a. So for the limit to exist, we know that a squared minus 8 must equal the same thing as 2a. Let's solve for a there. Let's get 2a on the other side. We would have 8 squared minus 2a minus 8 equals 0. It's quadratic. We can factor this. There's two numbers that multiply to negative 8 add to negative 2. So a minus 4, a plus 2 equals 0. So this tells me a is equal to 4, where a is equal to negative 2. I think that we have a problem though. And the reason, oh, no, we don't. I was thinking that the equal to part was for that second equation. If that was the case, then we would have a problem because f of a would be undefined. So let's look at what f of a is. Well, it depends. And maybe, and let's just check this too. If we plug in 4, where we see an a in here, we would have a squared, 4 squared, which is 16 minus 8. That would give us back 8. If we plugged in 4 into this equation, we would have 2 times 4, which is 8. Okay, so those both gave us the same number. Same idea, if we plugged in negative 2, just checking it, negative 2 quantities squared is 4, 4 minus 8 is negative 4. And if I plugged in -2 into this equation, 2 times -2, that is -4. So those both work, but we need to show that it's continuous. So let's show that f of 4 is 8. Well, when x is a, which is 4, it tells me to plug this into my first equation. I'm plugging in that first equation. Notice that we're going to get back 8. We get 4 squared, which is 16, and 16 minus 8 is -8. Okay, so the limit as x approaches 4 of f of x is equal to -8, which is equal to f of 4. So that's what needed to hold in order to be continuous at that value. And the same thing, do that for 2. So the limit, or -2. So the limit as x is approaching -2 of f of x. We saw that both sides, we got back -4. So this is -4. And if we plug in -2 wherever we see an x in that function, -2 squared minus 8 is also -4. So we found multiple values, what a needs to be in order for f of x to be continuous at a. F of 4, I said, was -8. I said it was 8 over here. Oops, 8 over there, but I wrote it down wrong. That was +8 right here. This should be +8. This should be +8. Right, because if we square 4, that's 16. 16 minus 8 is +8. Okay, so looking at the graph of the function, the original function f of x, we want to determine if the following is positive, negative, or 0. If we're looking at f of a, well, you're looking at your graph. This is f of x, and I can see that f of a is falling below the x-axis. So I know that this number in here is going to be less than 0. So for b, we're looking at f of b. If you look at f of b, notice that falls above the x-axis. And so that number I would get back would be a positive number. It's greater than 0. F of c, it's above the x-axis. And so that number is greater than 0. So now looking at the derivative and interpreting the derivative based off this function, we know the derivative is the slope of the tangent line at that point. Well, if I drew a tangent line at that point A, f of a, that would be a horizontal line because we have a minimum there. And so I know there my derivative then has to equal 0. F of b, notice that our slope of that tangent line, that's positive. It's an increasing function. So we know that this has to be greater than 0. The derivative at c, this is less than 0 because it's a decreasing function right there. So the double derivative. So taking the derivative of the derivative, let's see. Let me think about this for a second. So let's look at the concavity here. We are looking at the double derivative at f of a. If I look at this, notice that this is concave up right there at a. And so if our function is concave up at a point, then it's going to be greater than 0. So the double derivative of b, at b to me, this looks like this is where it's changing concavity. So notice how it's concave up in here, and now it's going to a concave down function. And so if I'm changing concavity, remember that's where our double derivative was equal to 0. That was an inflection point. And then that concavity here is concave down at C. And if our function is concave down at a value, then it's less than 0 for the double derivative.